Hello students, in today's video we will discuss about interpolation and we will try to derive the formula for Lagrangian's interpolation. So if we have a function y is equal to f of x, then the process that will estimate the value of dependent value y for a value x in the range x1 is less or equal to x is less or equal to xn is known as the interpolation. That means suppose if we are given with the set of points, say for example we are given with the points as x and y. For example, x is 1 and we are having the y value as some a, and at x is equal to 3 we are having some y value as b, and at x is equal to 6 we are having some y value as c. That means at every point of x we are having certain value of y. So to determine this value, this dependent value on x, or to determine the value of the dependent value from the x is known as the interpolation. Now there are two ways to find the function of the interpolation. Number first is for the equally spaced and number second is for the unequally spaced functions. Equally spaced functions means that when this space is equal, that means when, for example, here 3 minus 1 is equal to 2 and 6 minus 3 is equal to 3. That means the space here is 2 and 3, which is not equal. So we can say that this is the unequally spaced function. When we try to derive the polynomial for unequally spaced function, at that time we use two methods. Number one is the Lagrangian's interpolation. Number second is the Newton's divided difference. So today we are going to discuss the Lagrangian's interpolation. First we will try to derive the polynomial for Lagrangian's interpolation. So in order to derive the general formula for Lagrangian's interpolation, we consider the second order polynomial of type y of x is equal to a1 x minus x2 x minus x3 plus a2 x minus x1 multiplied by x minus x3 plus a3 multiplied by x minus x1 multiplied by x minus x3. If you will see, this is the second order polynomial. If you will multiply it, the power of the x is x raised to the power 2. So it's the second order polynomial. So we will consider this polynomial in order to derive the Lagrangian's interpolation formula. So we are considering this polynomial and we are considering that it is passing through the points x1, y1, x2, y2 and x3, y3. That means this polynomial is passing through the 3 points where a1, a2 and a3 are unknown constants whose values can be determined as follows. So we have to first evaluate the value of a1, a2 and a3. When we will first evaluate the values of a1, a2, a3, as these are the unknown constants, we will try to evaluate them and then we will put their values in the same equation. So we will put this equation as equation number first, then we will evaluate for the values of a1, a2 and a3, and then we will again put the same values of a1, a2 and a3 in this equation and we will get the Lagrangian's interpolation polynomial. So for example, at x is equal to x1, when x will be equivalent to x1, this polynomial will be equivalent to y of x1. So suppose this is equivalent to x, we are considering as x1. Therefore this polynomial will be equal to y of x1. Here it will be equivalent to a of x1 minus x2, x1 minus x3, x1 minus x1, x1 minus x3. Here we are getting x1 minus x1, which will be equal to 0, so the whole term will be equal to 0. Here again we are getting at x is equal to x1, this term as 0. So therefore at x is equal to x1, y of x1 will be equal to a1 x1 minus x2 x1 minus x3. So when we evaluate this for a1, so a1 will be equal to, suppose y of x1 is equal to y1, therefore we consider it as y1 divided by this whole, that will be equal to x1 minus x2 and x1 minus x3. So a1 will be equal to y1 divided by x1 minus x2 multiplied by x1 minus x3. Similarly, at x is equal to x2, y of x2 will be equivalent to a2 x2 minus x1 multiplied by x2 minus x1. So which implies, if we will solve this for a2, which will imply a2 will be equivalent to y of x2 divided by x2 minus x1 multiplied by x2 minus x3. So at x2, we will consider that y of x2 is equal to y2. So a2 is equal to y2 divided by x2 minus x1 multiplied by x2 minus x3. At x is equal to x3, y of x3 will be equivalent to a3 x3 minus x1 multiplied by x3 minus x2, which will imply that this a3 will be equivalent to y of x3, which will be equal to y3 divided by x3 minus x1 multiplied by x3 minus x2. So when we substitute this, the value of a1, a2 and a3 in the polynomial which we have considered earlier, that is this polynomial, when we will place a1, a2 and a3 in this polynomial, we will get the y of x function as y of x is equal to y1 multiplied by x minus x2 multiplied by x minus x3 whole divided by x1 minus x2 multiplied by x1 minus x3 plus y2 x minus x1 multiplied by x minus x3 whole divided by x2 minus x1 multiplied by x2 minus x3 plus y3 x minus x1 multiplied by x minus x2 whole divided by x3 minus x1 multiplied by x3 minus x2. Using the product and summation notation, the above expression, though that expression which we express it, can be written as y of x is equal to summation of I is equal to 1 to 3, because we are having the y value from 1 to 3. That's why we are saying it summation of y from 1 to 3 yi product of x minus xj divided by x minus xj, xi minus xj, where j is equal to 1 and j is not equivalent to I, which is the second order polynomial passing through x1 y1 x2 y2 and x3 y3. So this is actually the Lagrangian's interpolation polynomial. So in general we can say, if we have to calculate it for the endpoints which are unequally distributed, so we have the polynomial of degree n minus 1. So we can generally write it in the form of the product and summation as y of x is equal to summation of I is equal to 1 to n y of I and the product of the terms x minus xj divided by xi minus xj, where j is not equal to I. If you will see in our below terms, j is never equal to I. Here we are having x1 minus x2, x1 minus x3. We are not getting here as x1 minus x1, because that will be equivalent to 0. Therefore the whole term will be equivalent to 0. So we are not considering that. So this polynomial is known as the Lagrangian's polynomial. Now, as Lagrangian's polynomial is merely the relationship between the two variables, therefore by taking y as the independent variable, we can write the formula giving x as the function of y as follows. So if we will reverse the thing, like we will take y as x and x as y, we can say that as the Lagrangian's inverse polynomial. So this is the formula for Lagrangian's inverse polynomial. We are just placing the value x at the value of y and y at the place of x. That's how we are getting the inverse of the Lagrangian's polynomial. So Lagrangian's polynomial is used to find any value of a function when the tabulated values of the function are not equidistant. So it is always used when we are having the unequally spaced functions, and to find the values of an independent variable corresponding to a given value of a function. Now we will try to take an example and we will solve that using the Lagrangian's interpolation formula. So for example, we are given the table of the values as, for example, we are given with the table of values as this. Here x is equal to 0, 1, 2 and 3, and y of x is 0, 2, 8 and 27. At x is equal to 0, y of x is equal to 0. At x is equal to 1, y of x is equal to 2. At x is equal to 2, y of x is equal to 8. At x is equal to 3, y of x is equal to 27. Now we have to evaluate, we have to find it for 2.5. We have to find y of 2.5. See this y of 2.5, that means our x value is 2.5. It will lie somewhere here. So here it will be equal to 2.5. So that means it is again, here we are again getting it as the, here is the space of 1, here again the space of 1, here again the space of 0.5. That means it is an unequally distributed polynomial. We can apply the Lagrangian's polynomial here to get the value of y of x. We have to calculate the value of y of x because x here is equal to 2.5. So it lies somewhere here. That means we have to consider 4 points. We have to consider from 1 to 4 because 2.5 lies at the 4th point. So we will consider the Lagrangian's polynomial for 4 points. When we will evaluate the formula for the Lagrangian's 4-point formula, it will be as y of x is equal to y1 multiplied by x minus x2, x minus x3 and x minus x4. We have to calculate it up to the x4 values. We cannot go beyond that because we are given the value at x4. So we will go up to x4. So it will be y1. So the y terms will be from y1 to y4 and x term will be also considered from x1 to x4, and we have to put these points in the same Lagrangian's formula which we evaluated before. So the formula will be equivalent to y1 x minus x2 x minus x3 multiplied by x minus x4 whole divided by x1 minus x2 multiplied by x1 minus x3 multiplied by x1 minus x4 plus y2 x minus x1 x minus x3 x minus x4. So see, here we are not taking the x2 term. See, we are just taking x1, x3 and x4. So divided by x2 we are taking into the denominator x2 minus x1, x2 minus x3, x2 minus x4. Similarly, we have to go to the next term, that will be y3, that is plus y3 x minus x1 multiplied by x minus x2 multiplied by x minus x4 divided by x3 minus x1 multiplied by x3 minus x2 multiplied by x3 minus x4 plus the fourth term y4 multiplied by x minus x1 x minus x2 multiplied by x minus x3 whole divided by x4 minus x1 multiplied by x4 minus x2 multiplied by x4 minus x3. So now we have to consider it up to the 4 points. Why are we considering it up to the 4 points? Because we have to calculate y of 2.5 which lies at the 4th point. So we have to go up to the 4th point only. So when we consider it, we have to just put the values of x's and y's in the formula. So here we have y1. See, y1 is equal to 0. So y of x is equal to 2.5. So that means y of 2.5 will be equivalent to 0. The value of y1 is this term. So this is our y1, this is our y2, this is our y3 and our y4 is 2.5. So when we will put the values in this will be equivalent to 0. y1 is equal to 0 multiplied by x, the value of x is 2.5 which we have to calculate 2.5 minus 1, the value of x2 is 1, so it is 1. So similarly we are putting the values of x1s and x's and y's in the formula, and after putting the values in it we will get the answer as 15.313.